Our next kind of reaction that we're going to practice writing are for single replacement reactions. And these are like my favorite reaction type because I think, oh my gosh, the relationship drama of it all. This is the cheating type of a situation where I have a single person coming into a couple and kicking out somebody from the couple. One thing to keep in mind for these single replacement reactions is these are all involving ionic stuff. And when I say ionic stuff, I mean that the couples will be ionic couples, which brings me to the first thing of importance is that if my single person is a metal, right, the metal will try to kick out the metal in the compound, okay? So the reason for this is because my compounds or my couples must always be between a metal and a non-metal. I cannot have a compound of two metals. No two red things. I also cannot have a compound of two non-metals. No two blue things. Okay, so I've kind of got to be aware of what my single element is and be like, okay, who are you going to replace in this compound? Okay, so I have two options here, okay? I can have a metal trying to replace a metal. Okay. And on my activity series, which if you are in my class, we have our own activity series as a reference material on the back of our periodic table page. I've also written a little picture of our activity series here, right? So these are the metals. The metals in the activity series are written on the left side. So I will color them red. And then my short little list of non-metals are written over here on the right side. In my activity series, there's an arrow going up because the activity series is written in order of increasing activity. And what I mean by increasing activity is I mean that the higher up you are on this list, the more active you are. You're like, what does that even mean to me? Well, I like to think about it as attractiveness. This is the who's hot and who's not list of my elements on the periodic table. The most attractive metal is my lithium, and the least attractive metal, oddly enough, is gold. You're like, well, what does this even mean? Let's think. Let's say I am in a couple, and I am with somebody, and I like them. They're okay. But somebody else comes in, a single person, who is more attractive than the partner I'm currently with. You will want to kick out your old uglier partner for the more attractive option, right? This is so harsh. This is not my personality or anything like that. But this is basically what's happening here, and it does help us kind of remember things. So it says a metal that's located above another metal is prettier, so it will replace that other metal in a compound. But if the single element metal trying to come in is not as attractive, is lower on the activity series than the element he's trying to replace, it's not going to happen, right? That person in the couple is already like, no, I'm already with the more attractive person. No, thank you. You may not break up my happy couple. So in this case, I can write a no reaction for my single replacement reactions if the activity series does not support it. Okay, I feel like I've done a lot here. So let's kind of write up here some options of what I can see. So on my little skeleton, I've written two skeletons here. I've written one here and one here. That's because I want to show both types of when I have an option of a metal replacing a metal and then eventually a non-metal replacing a non-metal if I'm to utilize the other side of my activity series. Okay. So in this case, my metal is a single person, which means when he's coming into this couple, he's going to try to kick out B. If he is higher on my list than B, then he will, and he will be the new person who is in a relationship with my non-metal C, okay? So B has been kicked out. Okay, so we love that. We can totally do that with metals as long as the single person coming in is more active or higher up on the activity series. I can do the same thing with non-metals, you guys, but I just got, my non-metals are going to replace non-metals. Okay, and if you'll notice from my list, all of these non-metals on the activity series are halogens. So when I say halogen, that's what I'm meaning. It's just the non-metals that are able to play this game of single replacement reactions. A halogen that's located above another halogen will replace the lower halogen. He's more attractive. He will be favored in a couple. But if the halogen coming in is lower or below the halogen that's already in the couple, it will not replace it. So I would have no reaction in that case. So on my little skeleton, my second skeleton type, my single person in this specific case is going to be a nonmetal. So we say, hey, what if A is a nonmetal? You're like, that's cool. Well, BC always has to be an ionic compound. But here A is not going to kick out B, because if he tried to kick out B, then I'd be trying to make a couple between A and C. No, we don't do that. It's got to be an ionic couple, right? So A is going to try to kick out C. And if A is prettier or more attractive, that will be successful to where B is like, yeah, I'll join up with you, A. That's nice. You're way more attractive than C was, right? Yeah? So that's super fun and exciting. Okay, I'm going to bounce down to purely the document camera so we can chew through some more of these examples and talk a little bit more about this who's hot and who's not list of the periodic table. Gosh, this is so harsh for us. That's okay. Okay, so we talked about all this fun stuff. We also said this is all ionic stuff, which we love. When we learn about redox reactions, these are all redox reactions, single replacement reactions. I do not want to talk too much about that right now because redox is a big old beast that we're already learning a lot here today. I don't want to add some more onto that, but that will give us a little preview when we do talk about redox, that they're single replacement reactions usually. Okay. So what I'm doing here is I'm basically, kicking people out of couples and all that super fun stuff. Okay, so I'm dealing with single people and couples. Okay, I feel like something that we've been saying a lot so far with our previous two types of chemical reactions of synthesis and decomposition. We are really looking out for those diatomics, right? Diatomics. If I've got a single person, it is a diatomic. He comes in twos. We know that to be true, right? We are also, since these are all ionic compounds, we are going to cross if I need to make a new couple, right? And notice I'm saying new couple. We are also not going to bring our baggage from our previous relationships, which means I'm not going to bring any subscripts over from the reactant side over into the product side. And so I'm going to say get rid of old subscripts. Yep. So those are our kind of mentalities that keep us kind of grounded on knowing what to do. So let's look through a few of these examples and we'll do our coloring and thing, and you'll be like, and we'll checking our things. We'll be checking it on our activity series to see if the reaction will occur, and then we'll do some practice examples together. Okay, so magnesium turnings are added to a solution of iron 3 chloride. So here I have magnesium. Oh, he's a metal. So in my compound of iron 3 chloride, that magnesium is going to attempt to kick out who? The other metal. If you want to think about it as girls and guys, the reds are the guys, right? And the blues are the girls, okay? So that guy's going to try to get rid of the other guy and get with the girl here. Well, I got to see if magnesium is going to be successful, meaning I got to see if he's prettier or more attractive if you're a guy, more handsome than the iron. So we're going to look to my activity series and find magnesium. He's right there. And then my iron, where's my iron? Oh no, iron is uglier. Magnesium is more attractive. So yes, this reaction will totally occur to where that's why I see iron over here. Oh, he's so sad. He has been broken up with. Now magnesium gets the girl, gets the chlorine. Yes? Amazing. Okay, another example. I got sodium is added to water. Sodium. He's a metal. We mentioned before that if we're wanting water to be represented as a couple, meaning between two ions, I can write him as HOH, where I will have hydrogen be like the metal cation, and hydroxide, that polyatomic ion, be like the non-metal anion, the guy and the girl. So that means also that sodium is going to try to kick out hydrogen, right? The guy is going to try to kick out the other guy. We got to see if he's going to be successful. Hold on. I don't even know why I drew that arrow. I do not know if it's going to happen. I got to see it on the activity series. Sodium. Oh, wow. Okay. We up here sodium. And then hydrogen. Where are we? Oh, down there. Oh, no. Hydrogen is not as attractive. So that means sodium. Yeah. He's going to get the girl, right? So sodium, I now have a new compound between sodium and hydroxide where hydrogen is off on his own. Okay. Looking good. Now let's do this situation, the last little example here, with my metals trying to replace. I've got copper coming in hot here, and he is trying to replace the hydrogen in my HOH water compound. But let's see if copper will be successful. Copper, he is down here. Hydrogen is actually one step prettier than my copper. So if the prettier person is already in the couple, no reaction will occur. And you will love when you get a no reaction equation because you don't have to do anything like balancing or writing your products, which is wonderful. So these are examples of when I have metals replacing metals or hydrogen. If you'll notice, hydrogen in ionic compounds, when he's an acid, likes to play ionic with making a positive cation charge. But here also we can have nonmetals replacing nonmetals. Okay, so our example here is chlorine gas is bubbled into a solution of potassium iodide. Chlorine is a nonmetal in this case. So in the ionic compound of potassium and iodine, chlorine girl is going to try to kick out the other girl. Let's see if chlorine is prettier than the girl that is currently in there. Chlorine and iodine, who's prettier? Chlorine's up here, iodine. Ooh, iodine. No such luck for her, which means, yeah, chlorine is totally going to kick her out, right? So bye, iodine. And now I have a new compound between potassium and chlorine. Yeah, this is so harsh. I promise I'm a nice person, but sometimes in chemistry can be a little bit harsh sometimes. Next one, I got iodine trying to replace potassium, or trying to disrupt the happy couple between potassium and chlorine. So iodine, since he's a nonmetal, we have to see iodine or chlorine together, which I think we just compared these same two examples before, but that is okay. Iodine is not as pretty as chlorine is. We know the more attractive or the more active element stays in the couple, so that will not create any sort of reaction. Amazing. Okay, so now let's do it all ourselves. Remember, diatomics for single people, if you have them, my Hofbrinkels. Remember, forming compounds, we have ionic crisscross, right? Do not bring any subscripts from the reactant side over into the product side. Okay, I'm pumped about this. All right, for these first few examples, I've given you the formulas for the reactants. You would, just given this, you would know I'm trying to do a single replacement reaction because your reactants are a single and a couple. The option for you is to be like, okay, somebody going to replace somebody else, which means you pull out your activity series. You're already ready to go because you know what's going on. Okay, so I got zinc and I got hydrochloric acid, right? So zinc is a metal. This is always super important for us to figure out who is going to try to replace who. So remember, in an acid, that hydrogen is acting like a metal, which is why you see hydrogen on the red side of my activity series with the other metals. Okay, so now we got to see if he's going to be successful here. So zinc and hydrogen, who is prettier? Now I'm going to use my yellow one just so I don't have to keep moving my sheet up and down here. So what am I looking for? Zinc. Yep. And hydrogen. Oh, hydrogen is uglier. Zinc, get on in there. Yes. So I totally am going to have zinc kick out hydrogen. But I got to construct the result of this breakup situation on the product side, okay? Do not bring any subscripts over. Luckily, I don't have any here, but if there were any 2s or 3s or whatever, those get discarded. I'm free before you make either a new couple or you're free after getting out of a couple. I kind of like to write the single person first because it's the one that requires less thought on my end, because I know if I'm going to form a couple, I got to do a crisscross in that. My brain needs to be involved in that. So who's going to be free? We have hydrogen. He's free, except diatomic. Hydrogen always comes in 2s. And then my second product is going to be the new happy couple between zinc and now chlorine. The metal always gets written first and the non-metal gets written last, okay? And I'm not just going to be like ZnCl. I got to set up a crisscross and figure out, based on their charges, what ratio of each ion I have to each other. So if you need some more space off to the side, I got zinc. He's always got a +2 charge. And chlorine, group 17, always has a -1 charge, like all of the halogens. Okay, so the formula or the ratio of the ions to each other to be neutral is a 1:2 ratio, so I will have ZnCl2. Yep. Yeah, that's perfect. Now we just need to balance, not a big deal. Okay, so looking at my balancing, it looks like I have 2 chlorines on this side. So how about I put a 2 in front of hydrochloric acid, which also then balances my hydrogens. So we have used the activity series to first of all figure out who is replacing who and if that replacement will occur. Single guys be free unless they are diatomic, which then you give them a 2. And then my couple formation, do not bring subscripts over, create your own subscripts according to the charges on their periodic table placement. Great, okay. So next one, I dropped my periodic table. I'm dropping all the things. Okay, we've got now a single guy, bromine. Where's my colored pencil? Where's my colored pencil? Bromine. Oh, he's a non-metal. We got a non-metal girl coming in here. So in this ionic compound between boy, sodium, and girl, chlorine, bromine's like, yeah, I'm going to try to kick you out, chlorine. But we got to see who is more attractive on my activity series list for my non-metals. Looking at bromine and chlorine, bromine is, bromine is less attractive than chlorine. So what do we get to write in this case? No reaction, which is great. I can stop there. I don't have to write formulas. I don't have balance. So we got a no reaction because bromine, the single guy trying to come in here, is less active or less attractive than the other guy already in a compound. Okay, now we're going to flip to the back. I'm going to flip to the back. My printer was a little bit wacky, which is why it's kind of smeary, and that is okay. We can do all the hard things, can't we? Okay, I was going to say I'm not going to do all of them. I don't know what I'm going to do. I'm going to do some of them. I will do whatever I feel like doing, and then I want you to maybe practice on your own a little bit more. Okay, let's do the next one. We've got fluorine. Fluorine is totally a non-metal, so he will kick out the non-metal, right? We're going to see if that will be successful. Is fluorine more attractive than bromine? Yes. So that reaction will occur. Let's tackle the free person. The free person who gets kicked out is bromine. Free, no subscripts on me unless I'm diatomic, and bromine totally is. And then I got a new couple that I got to make between sodium and fluorine. Sodium goes first. I got to set up a crisscross if I want to make sure I write my formula correctly. Sodium's got a +1 charge. Fluorine, do not bring that 2. That is previous baggage from his single life. He is now coming to this couple trying to look his best, right? So now I have a 1-to-1 ratio. So my formula for my new couple of sodium fluoride is NaF, okay? Balance at the end, I need a 2 in front of sodium fluoride to give me the 2 fluorines that I see on the reactant side, which means now I also need a 2 over here in front of sodium bromide to match my bromines and my sodiums. Looking good here, looking good here. Oh, good. I'm excited about this next one. Okay, my single person is a metal. So I'm going to be looking at the metal side of my activity series. And we know that that metal is going to try to replace the other metal in my ionic compound. Y'all are like, what is going on with all the letters of the alphabet here? It is always only a red thing and a blue thing. Remember, you should be looking out for your polyatomic ions. This is totally sulfate. He is a polyatomic ion who has a -2 charge, so he is acting like a non-metal anion also, and has the ability to make an ionic compound with cations. So looking at this here, I'm like, I gotta compare aluminum to copper on my activity series. Aluminum to copper, aluminum to copper, aluminum to copper. Aluminum's right there. Copper is, oh boy. Copper is not as attractive. Aluminum is more attractive. So yes, aluminum will kick out copper. Let's write free copper. I'm free. I'm free. Not diatomic. So that is what he looks like in his freedom. And then I'm going to make a new couple between aluminum and sulfate. I've got to set up a crisscross. Aluminum always has a +3 charge. And sulfate polyatomic. Remember when we were writing formulas with our polyatomic ions, we put them in parentheses, right? Because we do not touch that SO4, right? Anything that needs to come down as a subscript to represent more than one of that sulfate falls on the outside of that parentheses, which means I will have 3 sulfates for every 2 aluminums. So my formula is Al2SO43. Okay. Sorry, that crisscross setup got a little too close to my equation. That is okay for me. Okay, so now I got some balancing to address here, don't I? So for my balancing, what do we want to tackle first? I'm looking at that sulfate right here, and I'm like, I know I have 3 on the product side, so how about we pop a 3 in front of copper 2 sulfate to give us 3 sulfates there, which then means I need to maybe put a 3 on the product side to balance my coppers. I have not even looked at aluminum. What is aluminum situation? Well, I got 2 here. I might also maybe want to put a 2 there, and then we are balanced. Okay, next up, I'm gonna do one more, because this is actually kind of cute that I gave you the Roman numeral. We're gonna do one more before I go to some examples where I've given you words, okay? All right, so we've got copper 2. Now, normally you would just see Cu, but if copper is going to kick somebody out in here and make a compound, we know since copper is a transition metal and it could have multiple possible charges, I'm letting you know here that I want for you to make this copper a copper with a +2 charge if he is going to make a compound, or if you're going to make a compound with him. So looking here, I've got my couple between my metal, silver, and oh, hi, polyatomic ion nitrate, right? So nitrate. So copper's going to try to kick out silver. Let's see who is more active or more attractive. More active. Copper's right there. Silver is down there. Oh, copper is more attractive than silver. Okay, so he's totally going to kick silver out. We know silver, he's going to be free. I'm free. He is not a diatomic, so that's what he looks like. Copper is now going to make a brand new couple with nitrate, setting up a crisscross with a +2 charge that copper has that I let you know. And nitrate always has a -1 charge. So yes, if y'all want to get out your list of polyatomic ions, right? I have my list of polyatomic ions handy, so I need to remember what the charges of these guys are, right? Okay. So then I have my ratio of my copper to nitrate. I will have 1 copper and 2 nitrates. So that is what my product side looks like. I'm going to balance at the end. I see I have 2 nitrates on the product side, so I'm going to put a 2 in front of silver nitrate, my reactant. And then I'm going to put a 2 in front of silver. And then we are balanced. Okay, I know it's just lame that I'm leaving this last one to the end, but I feel like we're reaching some redundancy. I want to do some new things that make your brain work a little bit harder than the way we've been working. Okay, so I'm giving you words, which means I first want you to write the formulas of the reactants. And then you have to see on the activity series if you're going to do any replacing, and then if yes, you're going to write the formulas for the products. A lot going on here, but we are super smart. Remember, single people, diatomics, that's all you have to think about. Couples, crisscross, yes? So my single person is potassium. Yes, potassium. Oh, well, let's just go ahead. Potassium's a metal, so he's going to be trying to kick out whoever the metal is in the couple. So I've got water. Let's just real quick look at water if I write it this way. Yeah. So when I write it that way, if I want him to look like an ionic compound, we know that hydrogen in front of my hydroxide polyatomic ion is going to be the metal player in this activity series ranking. So we're going to see, well, first I got to write the formulas. What am I doing here? Potassium, single person. He is not diatomic, so boom, there he is. My water, love writing him like this, right? I'm going to go ahead and put some blanks to remind myself I can balance this later. So I'm going to be ranking potassium and the hydrogen to see who is more attractive or more active. Potassium, oh wow, he's way up there. And hydrogen, yup, he is uglier, so potassium will kick out hydrogen. So I got to write my free hydrogen. He'd be free, but he is diatomic, so he gets a 2. Then I'm going to write a formula for my couple made between potassium and hydroxide. So if I want to set up my crisscross off to the side, potassium is a group 1 metal with a +1 charge. Hydroxide is a polyatomic with a -1 charge. So my polyatomics in parentheses, right, is a 1-to-1 ratio. So I got KOH. The parentheses are not required here if I only have one of that hydroxide, but y'all remember, we love keeping those parentheses because it makes it so much easier in balancing when I just look at the hydroxides and not the individual oxygens and hydrogens and all that mess, right? So for the balancing here, I notice I have 2 hydrogens on the product side. I'm looking at specifically the hydrogen on the reactant side that is not in hydroxide, okay? So that means to get 2 of him, I'm going to put a 2 there. That then will make me have 2 hydroxides, which means I go yeah on my potassium hydroxide, which means I have to go yeah on my potassium. Okay, so that's amazing. Let's do another one. This is super fun. Magnesium and sulfuric acid. So magnesium is a metal. Let's just go ahead and write what he looks like. Cool. Definitely not diatomic. Guess what, guys? Your diatomics are only nonmetals, okay? Or hydrogen. Oh, hydrogen. Sorry about that. So we got magnesium. And then sulfuric acid. Oh, man. Sulfuric acid, sulfuric acid, sulfuric acid. Well, that's an acid. So an acid is always a crisscross between a hydrogen and something else. It's sulfuric acid, which means it is a polyatomic ion that ends in 8. I've got sulfate going on here. Sulfate is SO4 with a -2 charge. So putting SO4 in parentheses with the -2 charge on the outside, sulfuric acid's formula is H2SO4. Whew, lots of good work there. Okay, let's see if magnesium will replace hydrogen. Magnesium, will you replace hydrogen? Magnesium is up here, hydrogen is down here. Yep, definitely more active, definitely more attractive. He will totally get to make a new couple with sulfate. Let's write our free guy. Free hydrogen, woo, woo, woo. But he is diatomic, so he gets a 2. Coincidence, not because that 2 got drug over, because he gets a 2 always, right, when he is a single. So I'm going to make a couple between my magnesium and my sulfate. So out to the side, magnesium's a group 2. Sulfate still has that -2 charge. Crisscross, I have a 2-to-2 ratio or a 1-to-1. Magnesium, sulfate, right? Keeping those parentheses around my sulfate so I can balance them all as one thing. For balancing, let's see what I got here. Let's see what I got here. Let's see what I got here. You guys, are we balanced? I think we're balanced. This is amazing for us. So that is a balanced chemical equation. I'm gonna do number 9, and then I'm gonna do, what do I want to do? I want to do 11. Yeah, let's do that. That sounds great. Okay, gold, and then I gave you a 1. Not because that's technically how we would write it, but how else would you know what the charge is on the gold if he's going to try to make a couple? So that is why I'm giving that to you. But I do notice that gold is a metal, which is going to be important because in my acid, that means he will be trying to replace the hydrogen part, right? So gold, the symbol of gold is Au, not diatomic, so that's what you get with him, okay? And then hydrochloric acid is between hydrogen and chlorine. Okay, so I have HCl. Awesome. Who's prettier, gold or hydrogen? Wow, well, gold is down at the bottom, so I'm going to say that will not be successful. Gold cannot replace anybody in the activity series. So if that is the case, I get to write no reaction, which we love. Okay. I love the next one. The next one you will do on your own. But the next one that I will be doing with you, and I think this will be the last one I'll be doing with you because I feel like we've gotten a lot of good practice in here. So I've got tin. Tin is one of my transition metals, which is why that 2 may come in handy if I need to use it, right? So, but single tin, there he is. He's not diatomic. And then I got silver nitrate. Silver nitrate, the crisscross to make that compound, the crisscross to make that compound. How am I going to do that? Well, silver, he is a transition metal, but he always has a +1 charge, right? So silver has a +1 charge. Nitrate is one of my polyatomic ions. Nitrate is, oh, there he is, NO3 with a -1 charge. So for this guy, it is a 1-to-1 ratio. My formula for silver nitrate is just AgNO3. Keeping that polyatomic in parentheses because I know it may help in balancing, assuming this reaction will occur. Let's see if this reaction will occur or not. So I'm comparing tin and silver to each other on the activity series because tin, you guys, tin is totally a metal, right? So I got to kind of keep in mind, they got to be on the same list, okay? So I got tin and silver. Let's see where tin is. Tin is there. And then silver is, oh wow, silver and gold ain't very pretty. That's very funny to me. And platinum, oh my goodness. Okay, so tin is definitely more attractive or more active than silver, so that replacement will occur, right? To where silver is like, see you later, I'm free, I got kicked out. That is not a big deal. I am also not diatomic, so I get no subscripts dragged over. And then now I'm going to make a new couple between tin and nitrate. That is where this is going to be important, right? Because I'm telling you that that tin has a +2 charge. And when paired up with a nitrate that has a -1 charge, it will be a 1:2 ratio. So my formula is going to be SnNO3 2. Boom, boom. We are ready to balance. Yep. Okay, we're excited about the balancing. We are going to be like, okay, nitrate's my main guy with an issue. I need 2 of them, so I'm going to put 2 of them in front of silver nitrate. And then I need to put 2 in front of my silver. Amazing. I lied. I want to do the last one, which is really awkward. It means I've not done only 2 on this page, but you can survive. Okay, zinc and water. Zinc is a metal, so I'm like, cool, 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 cool. Remember, water in an ionic compound, if we're wanting to represent him as a player, as a couple here in these single replacement reactions, I'm looking at HOH, right? Where zinc will be replacing that hydrogen here, right? In the front, if you can. So I have zinc, plain old zinc, not diatomic. And then I have water written as HOH. Yep. Let's see if zinc will be successful replacing hydrogen. Zinc, 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 zinc. Boom, he's right there. Hydrogen is, yep, not as attractive, so zinc will be replacing. Let's kick out hydrogen first. I'm free, but he is diatomic, so he is 2. And then my formula, or my new couple, is going to be between zinc and hydroxide. Zinc always has a +2 charge, right? So my formula for determining the ratio will be between zinc with a +2 and hydroxide with a -1. So my formula for zinc hydroxide is ZnOH2. Putting my blanks in front of everybody so I can balance, right? We need 2 hydroxides over here. So I put a 2 in front of my HOH, my water, which then resolves my hydrogens also. So these are my single replacement reactions. I know a single replacement reaction when I see it coming because I'm looking at a single person and a couple. We are going to see if the replacement occurs using our activity series, right? And if the replacement will not occur because the single person is not higher than the person currently in the couple, we get to write no reaction. I love thinking about this in terms of like attractiveness of couples. That's super harsh, but it is super helpful for me. So yes, we use our activity series for these single replacement reactions.